All right. Chapter 3. The biggest concept in Chapter 3 is a concept called equilibrium. And this is going to be the concept that we use over and over again, really from now until the end of the semester. We'll use it a lot in statics. We'll use it a fair amount in strength of materials when we start talking about, hey, we're doing shear moment diagrams, we're starting to analyze beams and whatnot. Equilibrium is a very important concept. Equilibrium plays off of what we talked about excuse me, in Chapter 2, and that is really there's two ways that a body can be moved. A body can be translated, that is, moved in a straight line, if all the forces act through that body or that point. But we just also talked about how a body or a point could be rotated about. There could be a rotational effect called a moment. So here's basically what equilibrium is all about. Equilibrium says this. It says when I look at a point or a body, I don't want that point or that body moving translationally. I don't want it moving left or right. I don't want it moving up or down. That makes sense if you think about structures. If we design our structures, we want them to be in equilibrium. They're not bouncing around, moving up and down. They're where they are. Okay? Because every force can be thought of in an x direction and a y direction, or x component and a y component. Equilibrium basically states that if we sum all of the forces on our body in the x direction, they better sum up to be equal to 0. I better not have any net force in the x direction. Just like the x direction, if I look at all the forces in the y direction, those two better sum up to be equal to 0. My body, my element, my particle, whatever I'm looking at, we don't want it moving translationally. Okay? Again, remember the forces have their own sign convention. Up, I'm going to say is positive. To the right, I'm going to say is positive. Down is negative. To the left is negative. Sort of keep it sort of like the quadrant system. All right? There's also, though, this rotational aspect that a body can have. And we talked about this. We call it a moment. If I look at a point, I can have a rotational effect caused by possibly a force times a distance. And it rotates or causes a rotational effect about a point. That's called a moment. So when I look at a point on my body, let's say just call it point A, all right, the sum of the moments about point A have to be equal to 0. I can't be standing at a certain point in a building, and when I stand at that point, the forces cause that point to spin around and start rotating, right? I got to be in equilibrium. So the point is optional. I'm allowed to choose whatever point, but whatever point I'm looking at on my body, I better have it such that the moments about that point equal 0. No rotation. Now again, I'll emphasize this, that when we talk about moments, remember this has a different sign convention. We're going to say positive is clockwise, and we'll say negative is counterclockwise. Okay? Don't get those two sign conventions, the one for forces and the one for moments. Don't get those mixed up. Okay? So that's equilibrium. And equilibrium, really is a basic concept. All right? We don't want our structures. We don't want our beams or whatever we're looking at. We don't want them having net forces on them, because then they're moving translationally, or net moments on them, because if they have some moment on them, then it's rotating. Okay? So equilibrium is the cornerstone of statics. This is what we're going to use.